Good evening and welcome. Today we're going to cover section 13.1 and 13.2 together. Our two goals are going to be pretty simple. We're going to review Hooke's law and the conservation of energy with springs, so that should be pretty quick. And secondly, we're actually going to define what simple harmonic motion is. So first things first, let's remember what happens when you start stretching springs. We look up here in the top. When you stretch a spring, what happens? It exerts a force back towards the equilibrium. So when you stretch a spring to the right, the force from the spring is going to be back to the left. When you're at the equilibrium position, here in the middle, that spring is unstretched or uncompressed, so there's no force. So F is 0. And of course, if you compress a spring to the left, its force is going to be to the right. There are two key points though here that I want to talk about, and that's if you start up here and you let go of this mass, it's going to slide this way back to the equilibrium point, like it is here. And now it has a velocity, 0 potential energy from a spring. What happens? Well, it has a velocity, so it keeps going to the left. And it keeps going to the left until you reach this point down here at C, where all of that kinetic energy from a velocity here turns back into spring potential. And since energy, in our case, is going to be conserved, the compression over here on the left in part C has to be equal to the stretch up here at part A. That distance, that maximum stretch, or down in part C, that maximum compression, is going to be defined as our amplitude. Because what we're going to see in this section is masses being stretched. They're going to go to the left, through the middle, and then back to the left. And then now, what's going to happen? Well, you'll reverse the process. If you start at point C, the spring will push it back to the equilibrium position here. Now it has a velocity. It'll keep going to the right. Once you're back at part A, the spring is going to pull the mass back to the left, and it'll end up back here at point C again. So that maximum stretch, that maximum compression is going to be defined as our amplitude when that mass starts oscillating back and forth. It can be a positive, it can be a negative, because of course you can be to the left or you can be to the right. That amplitude will stay the same as long as friction doesn't take any energy out of the system. Now, two more definitions that you guys are probably familiar with are the period, T, and that's the time that it takes for the object to complete one complete cycle of motion. One complete cycle is from A through B all the way to C and then back to A. So from where you start, right here, and then all the way through one motion will bring you back to where you started. That's the time it takes for an object to complete a cycle, would be your period. The frequency is going to be the number of cycles per unit of time. Normally the number of cycles per second. So it's going to be our SI unit. So the frequency is how many times it happens in a second. The next thing we want to define or do now is actually define what simple harmonic motion is. Here, realize that the force is at a maximum here at the extreme at part A and part B, and it is 0 here in the middle. And as we go from A to B, that force diminishes until it hits 0 right here, and then it increases as you go away from that equilibrium position. The other kind of motion that's going to be simple harmonic motion and follow those kinds of rules in that pattern is when we look at pendulums. Right now, hanging straight down, these pendulums, those pendulums are in a nice equilibrium position. All right. What's going to happen is somebody's going to come along and move them out of the equilibrium position. So I hope we get a nice little side shot. There we go. Now, let's think about what's happening. The force of gravity, of course, is what's going to make these things swing. But what we got to notice is very important, and that's the force of gravity, since it's making something rotate, is really a torque. So right now, we have the force of gravity going down. There is an angle right here. We can calculate the torque if we knew that length right there. And it's going to make this pendulum swing back down. Well, when it goes back to the middle, it's going to be in that nice equilibrium position. Force of gravity will be pointing straight down, the radius will be straight up, and there will be no torque. So when we go back to the equilibrium, you're going to have no force, just like we did with the springs. What's going to happen? They swung through the equilibrium position, turning kinetic energy into potential energy, and then that potential was turned back into kinetic at some maximum amplitude over here. If we could keep looking, we'll see that that amplitude stays the exact same. That maximum distance both to the left and to the right of your equilibrium will be equal. So this again is another example of simple harmonic motion. As you guys can see, it's really pretty cool. So they kind of sync up and then they get out of sync and then get back to random. It's like synchronized pendulums. Should turn this into an Olympic sport. Man, that's pretty cool. Moving on. Problem number 2. When we have a 4.25 kilogram object, it's placed on top of a vertical spring. The spring compresses a distance of 2.62 centimeters. We want to know the force constant. So as you guys probably guess, we're going to have, oh goodness. Now I don't know what's going on. Ah, pen, yes, wonderful. Okay, so F equals kx. Well, what's the force exerted on the spring? And of course, what's the force of the spring? Well, the force is going to be 42.5 equals K times, oh gosh, 0.0262 meters. So K, we divide both sides, will be 42.5 over we'll call this like 26 times 10 to the negative third. So if we go back over here, we're going to get K equals 26 into 42, like 1.5, maybe 1.6 times 10 to the positive third Newton per meter. There we go. Again, an equation you guys should know pretty easily. The next one, we're going to do the same thing. Here we're going to have the load is 50 newtons, so that already gives us the force. It's attached to a spring, and the spring stretches 5 centimeters. If the spring is now placed horizontally on a table and stretched 11 centimeters, what force is required to stretch the spring by that amount? So we know what we want to use, of course, is F equals kx, but we don't know k. So let's solve for k. We know that when 50 newtons is exerted on it, we're going to stretch the spring 0.5 meters. Oops. So divide by 5, you get 10 times 10 squared, and this gives us 1,000 Newton meters equals K. So now we can do part A. Now we want to know the force required to stretch the spring 11 centimeters. So now we're going to solve for F. We know that K is 1,000, and our delta X is going to be 0.11. So this will give us 110 newtons. We want to plot a graph of force on the y-axis versus spring displacement from the equilibrium position along the x-axis. That's really going to be like y equals mx plus b. B is going to be 0 because if you stretch the spring 0 centimeters, you're going to have 0 force. It's our real equation. So F is taking the place of y, and x is still x. So what's k? K is 1,000, so that's really like your slope. So you're going to plot y equals 1,000x. Now, just as a quick reminder, when you do stretch a spring, you're going to have potential energy. So if a block here slides into a spring, it has kinetic energy right now. As long as there's no friction, this block is going to compress the spring. At this point, we have not fully compressed it. We still have a velocity. What does that mean? It means our energy is both kinetic and spring potential. Here at point C, we have pure spring potential, so our energy is just that. And if this spring pushes the block back out, again, assuming no work done by friction, all that spring potential is going to be converted back into kinetic. Again, just a quick reminder of how we're going to see the energies in these problems. So let's take a look at what we actually want to do in the homework. We want to have a spring-loaded pellet gun. We're going to fire a 3-gram projectile at a speed of 45 meters per second. The spring is compressed to its maximum design difference of 8 centimeters. What spring constant is required? Well, we want to make sure that the kinetic energy we're going to get that kinetic energy of the mass from the spring potential energy. So that's why we're going to set up this equation. That mass is going to get its velocity from the spring potential. So let's start filling in the numbers. We get 1/2. M is going to be 0.003 kilograms times V squared will be 45 squared equals 1/2 times K times 0.08 squared. Oh goodness, so 40 times 50 is what we got to do right there. This will be 0.0015. 40 times 50 is 20 with 2 more zeros. 0.08 squared is going to be, that's a half by the way, is going to be 64, not 0.64, but 64 times 10 to the negative 4th times K. So if we divide both sides by 10 to the negative 4th, we get 15 times 2,000 equals 1/2 64K. I'm almost done. 20 times 15 gives me 30 with 1, 2, 3 zeros equals, what is this, 32K. So dividing 30,000 by 32, it'd be close to 1,000, a little bit less. So let's call like 9,000. Sorry, 900. Goodness. Cross that out. 900. Good. Units, Newton meter. Alright. And then for part B, use F equals KX. Alright. Part B is going to be, oh goodness, there we go. Alright, we want to know the maximum force required to load the gun. Essentially, what's that maximum force that corresponds to your maximum compression? So your force is going to be equal to KX. F equals 900 times 0.08. I'm going to take these two zeros away and make that 8. And your force is 72 newtons. There we go. So there's part B. And our last example problem of the day is going to be number 13. 13 is a wonderful one because we start involving two different chapters together. We're going to fire a bullet into a block. That block has a mass of 2 kilograms and it's attached to a spring. Here's its force constant. We're giving it right here. There we go. The mass of the spring is negligible, not the block or the bullet. We want to know how far the spring is compressed when the bullet has a speed of 300 meters per second just before it strikes the block. You must use conservation of momentum. What a wonderful statement. Let's think about this. We have two parts of this problem in my point of view. We have a collision, so we're going to have before the collision and after the collision. During the collision, energy is not conserved because it's an inelastic collision. When you shoot a block, a lot of the energy is used to deform the block and deform the bullet. So we have to use our conservation of momentum so that we can figure out the velocity of block and bullet post-collision. After the collision, the only force that's acting on the block and bullet is the force of the spring, and that is a conservative force. So this is 10 grams. Our mass is 0.01 times 300 equals. The mass after the collision will be 2.01 V. So take these two decimal places over to right there. Take those zeros away, and we get 3 meters per second equals 2.01 V. Divide by 2, we get 1.5 meters per second as V. What's that V? That's the velocity of the block and bullet post-collision. So what happens after the collision? The block and bullet move together and compress that spring. So what's going on? We're conserving energy. We're moving from kinetic energy to that's a 2. Spring potential. Just like that. Halves cancel. Our mass is 2.01 kilograms. Our V is 1.5 meters per second squared. K is 19.6. Whoops. 19.6. And we're going to solve for x squared. So 1.5 is 2.25 times 2 is 4.5 equals 19.6 x squared. We'll divide by 20, so it's 0.225 equals x squared. Square rooted. Whoops. No, what happened there? Alright, square rooted. I want to think about this as... Oh heck, how can we think about this? I like the square root of 225 because I know that's 15. So let's make that 225 times 10 to the negative 3 equals x squared. So square root gives me 15 times 10 to the negative 1 times the square root of 1/10. Okay. So this gives me 1.5 times square root of 1/10 is about 1/3. So this is 0.5 meters equals x. There we go. Alright guys, that handwriting has gotten really terrible. But we are done.